Hello, in this particular talk we're going to have a look at a couple of extensions to the basic steering behaviours. And these are things that can help further enrich the types of capability that steering comes along with. So we're going to be considering the notion of constraining our steering behaviour and also the notion of following a particular defined path. We'll start off first of all having a look at path following. So by path following, what we assume is that we have something that defines a path that's already available to us, and we want to get a particular game object to follow that path, to sort of etch it out, and we'll use the steering behaviours as our means of actually following the path. You can see an example of it here. Now, if you're thinking about a path, then you probably imagine yourself sort of walking along the path. That's fine. Within a game, very often the path is going to be sort of a line type of structure, or maybe a number of different points. So there isn't really the same notion of having a defined width to it. So the first thing we're going to have to do for a particular object is to work out whereabouts it is on the particular path, or what is the closest point to the path that it has. Depending on how we actually represent the path, this can be a very easy thing to do. It also potentially can be quite a difficult thing to do. Once we've determined the point on the path, then we're going to work out a point a little bit further down the path, and we will then seek towards that particular point. And we'll keep doing that process, updating each frame to work out our new position, determining a little bit down the path, and then seeking towards that particular point. So you see example here, we've got our object, we're mapping it onto the closest point on the path. We're then projecting along to determine our target location, and then we're seeking towards that particular location. And if this is a path that has a defined endpoint, we might decide to not to seek to the last point, but rather to arrive at the last point, so we're stopping when we reach it. There's a couple of different forms of path following, non-predictive and predictive. They're actually quite similar. We'll have a look at non-predictive first of all. It's more simple of the two approaches. Again, it's a delegating behaviour, so we're going to work out a target and we will seek or arrive towards that particular target. So we've got a method, follow path. Into that we're passing the object that is going to follow the path. And we're assuming that the path itself we have wrapped up within a particular class. So we have a class here called path that embodies or defines the actual path itself. We're also going to have a path offset, and this is a property that controls how far down the path we're going to seek towards. So if it's a very small value, we're sort of really looking just a little bit down the path, or for the next few steps. If it's a larger value, we're peering further down the path and seeking towards that point. Now, when we call the method, first thing we want to do is to work out, okay, well, whereabouts are we on the path? So we are assuming here that in our path class, we're going to have a method where I can pass in a position, and it will then return me the distance along the path that's closest to that position. So it's not a point here. You can see it's a scalar value, path position, a single float. So this assumes that we can describe our distance along the path, say for example a value between 0 and 1, where 0 is at the start, 1's at the end, 0.5 is halfway across, for example. Given that path position, we then work out, okay, let's go on, use the offset to step a little bit forward. And we're also assuming that we can go back to the path and we can say, okay, for this parametric value between say 0 and 1, what's the corresponding location or target location that we would have for that? Given this, we can then seek towards that particular location for the target in hand that's following the path. So nice and simple, reasonably straightforward. Certainly it's presented at this level, it's quite a high level. There's nothing complex to this. Arguably some of the more detailed and more difficult decisions is the actual path class itself and how it potentially represents a path. And we'll have a look at a reasonably simple way of doing that. Predictive path following is a small extension to the non-predictive. So here we're passing in the object and the path that we're following. We've still got a path offset. We also have another variable about how further ahead in time we're going to be considering our position. So predictive path following works out where, based on the current velocity, where we will be in a little bit of time, and then uses that future location to work out where we are in the path and where we should seek to. So it takes into account the velocity of the object, not only its position. So things we do, first of all then, is to work out, we know our current position, we know our velocity, we know how far ahead we're going to look. Let's give us our position based on the current velocity. And then thereafter, we're doing basically the same thing as the non-predictive. We're taking this future position, working out where that corresponds to in the path, looking a little bit further along the path, getting the position that corresponds to, and then seeking towards that particular position. There can be some problems with predictive path following. You can see it here in this particular diagram. So for the triangle down at the bottom, we've just gone around a corner, we've got a certain velocity. It's potentially true or valid that we would predict that our future location is going to be where the dotted triangle is. And if we have a path that has this type of looping structure, the future position, we might map it onto a position on the path that is quite far away from the current position. So you can see there we've mapped it onto the other side of the loop. I'm predicting a point ahead of that and then seeking towards it. So in this case, there's a danger with the predictive setup that we could miss out a complete loop on our path. Easy way of getting around it, and this comes into, actually was sort of mentioned in the last slide, we can pass in the current position, the parameter that determines how far along the path that we are. So this is our parametric value. And then whenever we get back the projected value, if we're using the current value, we can constrain that to be within a defined region of the path. So effectively, we can limit the things and the positions in the path that we can actually map onto. And that offers you quite a good way of making sure we don't skip or jump over things. Although sometimes, depending on the game, notionally if the object, for example, can teleport or things like that, we would want to have that skipping behavior. So it does very much depend on our game. It mentioned that the path, there's different ways we can do it. We've got a class, we've got a few methods we want to ask of that class, and some of the ways of defining paths actually can be quite complex. We can describe them mathematically in terms of a number of curves that can be combined together, which is fine. There is actually a fairly simple, somewhat crude, but actually quite effective way of doing it. It is to use a list of points. So here we have an underlying curve, and we're mapping out that curve as a number of representative points along the curve. And you can see here that if we have a straight portion of the curve, or near straight, we don't need too many points. But around the corner where we do have a greater degree of curvature, there we've got a greater density of points being represented. The nice thing about this structure, if I want to work out, well, whereabouts am I on the path? Given the input parameter, I can simply go through my points, work out how far away I am from each of the points, and then pick the one that I'm closest to. And predicting the future location, I use the next point in the particular series. So again, it's quite a simple, nonetheless effective way of representing a path that we could pass off to a steering algorithm. That's all we need to say about path. There's not really a huge amount to say, but we'll look at path finding in a later lecture, which is all about how we actually plan out and determine a route, and that route could comprise a number of different linear points if we would follow. Next thing we want to look at here is what's known as constraint motion. What is constraint motion? Why do we need it? The steering algorithms that we've been looking at, they output an acceleration or a velocity for the kinematic one. They make no distinction as to the direction that acceleration is in. They assume that the object that is using the steering can accelerate equally in all directions. And that isn't always going to be the case for objects. So for example, vehicles, things like cars, they can only accelerate in the direction in which their wheels are are pointing, so they have a forward acceleration only. If they have a backwards acceleration, the actual magnitude of these accelerations will change. They can't move sideways on their own accord. Equally, cars will have a maximum turning rate at which the wheels can change. So the motion is constrained by the physical device. And it's nice within things, for example, like racing car games, that we take that into account if we're using our steering algorithms. A couple of different ways of doing it. Filtering is probably the most easy way, which is where you go to your steering algorithm, you ask, okay, well, what output do you want? And you then cut away bits of that. You filter it based on the movement that you can presently realize. So here we have an example of a car. We might be seeking somewhere down towards the bottom right of this slide. So there we've got a requested linear acceleration, bringing us down, and a requested angular acceleration, turning us around. What filtering entails is that you simply say, okay, the car can only accelerate forward, and the car can only turn with a certain amount of rotational velocity. And you cut out of that anything you can't currently realize. So our requested linear acceleration in the blue arrow, we can only presently realize what the green arrow shows. We can accelerate forward with that particular magnitude, and we'll turn again as the green arrow shows. The nice thing about steering is because we're doing it frequently, multiple times a second, we're updating the object. As soon as we start to turn, then we can start bringing in this example, some of the downward velocity. And over a number of frames, we'll accelerate and turn towards the requested target, trying to match the particular acceleration that we've etched out for it. It works. It's actually quite simple, reasonably effective, but it does have some limitations. You can see the limitation here on the screen. This case, we have a output acceleration which is nearly perpendicular, nearly at right angles to the vehicle. So because we can only accelerate forward, we're chopping out most of that requested acceleration. So what that means is that the car will slowly accelerate forward until it is able to turn more around towards the target, and that probably isn't the type of behaviour that we want to exhibit. The more sophisticated way of, and a very effective way of doing this, was used as known as movement arcs. So you can see an example here. We have a couple of arcs. We have a front arc and a rear arc, and the rear arc has a defined maximum length, and outside of that we sort of just assume the front arc wraps around everything. If we have a target and that target falls within the front arc, then we turn towards it and accelerate towards it. We do the turning and the acceleration, and we accelerate really as fast as we can then towards that particular target. If the target falls within the rear arc and whatever distance we've defined for the rear arc, then in that case we will reverse towards our particular target. So that covers a few of the situations. Now the interesting thing about this is that as the car increases in speed, the front arc and the rear arc shrink. They get smaller. And what we have appearing between them is what's known as a braking arc. And the faster the car goes, the bigger the braking arc goes, the smaller the reversing and the smaller the front arc becomes. The nice thing about this is that, okay, the front arc and the back arc still have the same properties. If you have a target, though, that falls within the braking arc, then you don't accelerate towards it, and rather you brake the car, you decelerate, and you turn towards it. So effectively the car slows down and turns. You need to think about this dynamically. Because the car is slowing down, that means that the arcs, the yellow arcs, will shrink. So the slower the car is going, the smaller the yellow arcs actually are, until such a point that the front arc and the rear arc actually touch, that the yellow arc completely disappears. And it gives you a lovely setup. So if it's in front, in the green arc, you can just continually to turn and accelerate towards it. If it was in the yellow arcs as your indication that you really need to slow down and turn towards it, slowing down will reduce the size of it, will increase the size of the front arc, and we'll get to a point then where the target actually falls within the front arc, and we can then start our acceleration towards it. By way of takeaways, a couple here. We can use our basic steering behaviours, do a little bit of extension to them and turn them into something we can use for path following. Likewise, we can build upon the output steering behaviours and put in some form of activation or motor constraint on it, so that the objects we're applying the steering to, that they can be constrained to move in ways that are appropriate to whatever physical object they happen to be representing.